Hello, I'm Paul Campbell. Welcome to my channel. As many of you will know, I shoot these videos on the old Canon C100 cinema camera, which is now 12 years old. It shoots only in 1080 HD, but that's perfectly adequate for my purpose. Up until now, I've used the Canon Wide DR profile, that's wide dynamic range. It's easy to expose and gives a slightly flat result that can easily be adjusted with a little extra contrast and saturation to taste. For the current video, however, I'm using Canon Log. That's the original Canon Log. It's been through a few improvements since then, but only the original Canon Log is available on the C100. For convenience, I'm using a LUT from AbelCine. It's the AB Norm Log to Rec 709 full range LUT. It's a bit dramatic, but I do love dramatic images. Even so, I've dialed it back. I've dialed back the saturation quite a bit, and I've dialed back the red a little using printer keys and Resolve. So, today I want to talk about parabolic reflectors and to give my opinion on parabolic softboxes. So, what is it about the parabola that makes its shape useful as a reflector? Well, let's have a look. First, just what is a parabola? Now, the Greek mathematician Euclid studied the shapes that could be obtained if you cut a cone in certain ways. Cut straight across, you get a circle. Slope your cut down or up a little, and you get an ellipse. Cut parallel to the edge of the cone, and you get a parabola. Cut vertically, and the result is a hyperbola. These four shapes are the conic sections. All of them give rise to three-dimensional shapes used as reflectors. Spherical mirrors are used as reflectors in astronomical telescopes. Now, spherical mirrors are not the best for this, as they do not bring light to a single focus. They are, however, easy to make and relatively cheap, and they're adequate for small mirrors with long focal lengths. Isaac Newton made the first reflecting telescope with a spherical mirror made of metal. Later, scientists perfected methods for making parabolic or paraboloid mirrors, which do bring light to a single focus. They're not perfect, however. They have a defect known as coma. The Hubble and other large telescopes have hyperbolic mirrors. Ellipsoidal reflectors are used in stage spotlights. And parabolic reflectors, as we know, are used pretty much everywhere, in torches, searchlights, car headlights, and in stage, event, and warehouse lighting. Now, apart from making a cone and cutting it up, there's a couple of other ways that you can draw a parabola, fortunately. Each conic section has a focus and a directrix, and they can be defined in terms of the focus and directrix. For instance, the focus is a point, by the way, the directrix is a straight line. Now, every point on a parabola is the same distance from the focus as it is from the directrix, measured perpendicularly. Well, that's all fine and good, but there is another way in which you can draw a parabola, and that's using a mathematical equation. The simplest equation is y equals x squared. There are many others, all quadratic equations. Now, for this parabola, y equals x squared, the focus is at 0.25 on the y-axis, marked here. Now, there are actually an infinite number of parabolas that we can draw. Here are just a few. You can see they range from very shallow, almost flat, to very deep. Now, here is the secret of the parabola. If you place a light at the focus, any ray of light coming from that focus point will be reflected parallel to the central axis of the parabola. This ray, for instance, will be reflected thus. Now, we can prove this by drawing an accurate diagram and using one of the laws of light, well, perhaps two of the laws of light. One of the first law of light is that light travels in straight lines, or at least it appears to. The second law of light is that when a ray of light hits a shiny surface at a particular angle, it'll be reflected at the same angle. Now, these angles are called the angle of incidence and the angle of reflection, as you can see in this diagram. Now, a perpendicular line has been drawn at the point of incidence so that the angles can be measured. This line is called a normal in mathematics. The angle of reflection here is equal to the angle of incidence here. Now, of course, with the parabola, we don't have a flat surface, we have a curved surface. But in this case, we can draw a grazing line to the parabola like this. Now, this line is called a tangent. And then we can draw the normal to the tangent and measure the angles of incidence and reflection as before. Now, coming back to our light rays in the parabola. Any ray of light, as I've said, any ray of light from the focus is reflected parallel to the principal axis. This one, for instance, and this one. So the parabolic reflector very efficiently gathers all the light going off to the sides or behind the light source and directs it forward with none going off to the sides, in theory. But you might notice that rays of light like this one are going to miss the reflector completely and diverge from the central direction. If you want to minimize that, you can use a very deep parabolic reflector. Now, also, I did say in theory. You remember that the focus of the parabola is a point. And a point, unlike a real light source, has no size. So parabolic reflection, ideal parabolic reflection, will work best with very small light sources. Now, in the past, before LEDs, there were two types of light globe, the incandescent and the gas discharge type. The incandescent globe was pretty common domestically, and the gas discharge type is more of an industrial light source. It produces an extremely bright light more efficiently than an incandescent globe. Now, because these light sources, the incandescent globe and the gas discharge tube, are quite small sources, it's possible to position them fairly accurately at the focus of a parabolic reflector. Now, industrial and film applications use HMI tubes. HMI tubes are gas discharge tubes. And they're still used because they can produce far more light than any LED source at the moment. Now, HMI stands for hydrargarum medium arc iodide. Hydrargarum is the old name, very old name, for mercury. And these tubes contain mercury vapor and other vapors which have been chosen so as to give the light coming from this globe a color temperature approximating that of daylight. Now, incandescent light globes use a coiled filament heated to white light by an electric current. HMI gas discharge tubes create an electric arc inside a carefully designed gas, which causes the gas itself to glow very brightly. Now, here's an example of a film lighting unit which uses a HMI globe. It's the Aramax 18,000 watt PAR light. Yes, that's 18,000 watts. That should be enough to fry your eyeballs, probably. You can see the globe in there at the focus of the reflector. Now, PAR stands for Parabolic Aluminized Reflector. Now, the globe in this Aramax can be moved in or out, varying the focusing effect and changing the spread of the light. The spread can be changed between approximately 20 degrees and 60 degrees using this method. Let's see now what happens when we move the light away from the focus. Let's move it outward to this point, say. Let's draw a ray of light from this point and see how it's reflected. Now we could proceed by measuring the angles of incidence and reflection, but we can do a mental experiment that saves a lot of work. Look at how a ray of light from the focus is reflected at this point. As we already know, it'll be reflected parallel to the central axis, like this. Now look at our ray from the new point, here. It's at a sharper angle than the one from the focus, so it must be reflected at a sharper angle, like this. Now I think you can see that this will apply for reflection at any point on the reflector, and for a light source anywhere outwards from the focus. Light will be reflected inwards. It'll be converging. Of course, if you go away from the light a little, these converging rays are going to cross over and will be diverging instead. Now let's look at moving the light source inwards from the focus, say to this point. Look at a ray from this point now to the same point on the reflector as before. Now it would be the same to any point, but this is just to reuse the diagram. You can see now that the ray is shallower than the one from the focus, and so the reflection will also have to be shallower, like this. So it'll be diverging, spreading out. In photography, the Broncolor parabolic umbrella uses this technology, moving the light into and away from the focus of the parabola to control the character of the light. As with all photographic umbrellas, the light is directed into the umbrella. It's mounted on a shaft, which can be moved in and out in the same way as the globe can be moved in and out in the aramax described earlier. It's important, however, that the light used can project sideways as well as forwards, or it won't be illuminating the umbrella very much. Flat fronted lights will not work, because they'll only project into the bottom part of the umbrella. Now, Karl Taylor has a brief explanation of this. The link is in the description. Karl also has videos describing his use of the parabolic reflector, the Broncolor parabolic reflector, that is. Now, Karl's in the enviable position that he works for Broncolor, and that means he gets to use a $12,000 parabolic reflector for free. Now note that the umbrella does not have to be deep to actually be parabolic. Parabolas can be shallow or deep, as I showed you before. The key thing is that the light needs to be at the focus and ideally spreading into the parabola from all sides, just like it does in the aramax, where you've got a light globe sitting at the focus, and light from this light globe goes out in all directions. So, where is the light in a parabolic softbox? Well, it's right here at the bottom, and it's pointing out. So the majority of the light from it is escaping straight out without touching the sides, without being reflected at all. So this simply doesn't work. Okay, but it's a softbox, isn't it? So that means there's a diffusion screen at the top, and probably another one on the inside. Now, light rays don't escape at all. They just bounce around, and their function is to illuminate the outer diffusion material. This outer diffuser then becomes the light source. Light comes from the front of the softbox in random directions. I mean, that's the whole point of using a diffuser, to change directional light into non-directional diffuse light. So the outcome is that it doesn't matter how much focusing takes place behind the diffuser. The light from the front is still non-directional. So does it matter if the reflector is parabolic in the parabolic softbox? I'd say probably not. It is possible that the illumination of the front diffuser could be more even with a parabolic reflector, brighter at the edges than with a, say, a spherical reflector, but I haven't investigated this at this time. Perhaps later. Well, that's it for today. I have another video coming up on the optical snoot, which involves an ellipsoidal reflector and lenses to shape the light. It actually mimics a stage spotlight in many ways. Until then, goodbye, and as we say in Irish, slán go fóill agus go ndéirí an bóthaileat.